In this lesson, I'll be going through memory management. I'm not going to touch all of the virtual memory issues, but at least I will handle a lot of basic memory management. That is, how does the operating system map addresses of processes from virtual address spaces to physical address spaces, various techniques for placement, partitioning, and paging. Right. So there are about two parts to memory management. This is memory management. Virtual memory is slightly different. If you didn't understand any of the terms I was using, I'm hoping that at the end of this lesson, you'll understand a lot of the main ideas. You don't have to memorize everything, but I think it helps if you get the core concepts and then we build on them. So if you are into computers in any way, by now you should be familiar with variables, code, and the fact that processes or programs that are running actually use memory. And when it comes to memory, there are two views of memory. One view is what the process sees, which we usually would say is maybe the virtual memory space or the logical address space. And then there's the physical space. So on your motherboard, there's your memory hardware. So there's a way that it's seen, and there's also a way that your programs see the memory that they are working with. Right. Now we'll discuss various ways that partitioning of memory takes place. We'll also look at how operating systems try to place memory requests or allocate different sections of memory to different processes. And eventually we'll also look at paging. I'm missing a close bracket here. We'll look at paging, and in particular we'll look at three different approaches, but I think most people should at least be able to do the hierarchical. The hash page tables is, if you know about hashing, it's easy to apply, and inverted tables, they look a little bit like hashes, but not exactly. So I hope that at least we'll go through this. It's going to be a little bit long, but I'm hoping you'll understand a lot. I'm going to skip the learning objectives. I'm sure the lesson just will go through it. But the overview, everything in here, you should be able to expand on it. Alright, so let's look at memory. Now, throughout the course, or if you've been into computers in any way, one of the things we keep talking about is a CPU has registers. And the registers are usually the fastest type of storage it can access. It isn't a lot, but it's something that usually is used for computations, maybe adding numbers, subtracting numbers, multiplying numbers. And now and then programs need extra information, and it will usually come from memory. But it actually takes a while for data to go from memory to the registers. So what most people, or most hardware manufacturers, at least for the CPUs, will do is they'll put a little bit of memory, usually called the cache, on the CPU. So if you have a 4-core machine, there'll probably be 4 caches. Depends on the design, but every CPU, it's nice if it has a cache, so it doesn't have to spend so much time asking for information from memory. It doesn't look like it should take a long time, but it can delay. It won't be as bad as going to disk, but it will be slower. So I got some speeds here, 1 CPU clock. Usually the speeds here, I'm sure will, in future, I'm sure someone is watching this maybe 20 centuries from now or something. Well, that's too long. I'm sure by that time computers would have gone quantum. But maybe in 10 years we will be looking at this, and it may even be much faster. We'll be looking at maybe 1 terabyte speeds for cache. I don't know what will happen with hardware. We'll probably discover something that will just blow the lid off all the speeds we have currently. So this is just an example. So it's not to memorize the numbers, but just be aware that registers are fast, or what's the fastest. Cache follows. Memory is slower than cache. The disk will be slower than memory, and currently there seem to be 2 types of disks. The normal disks that we have with platters and spinning plates and so on, and we have solid state drives. The solid state drives work a little bit like pen drives, and they seem to be faster. And of course these days there are external drives, some of them on the network, and because of the internet we are also having some programs that actually work across the network, across the internet. So what I'm going to do is I'm going to pull up some data. Now I didn't compile the data. I just looked for someone who seemed to have a good list, and this was from GitHub jboner. That's the address at the top. You can take a look at it. I'll try and put it in the slides and reference it where possible, but I'm just making sure everyone sees and appreciates this. And what he does is to compile, and I don't even think he did it all by himself. He seems to have gotten some data from someone from, or maybe from Google Research, Jeff Dean and Peter Novick. So there are a few places, and he's compiled the whole list. And what he's done is to try and present some speeds. This is in nanoseconds. Now remember that most of your computers would have speeds of maybe, these days they would say 2 gigahertz of for the speed, for the CPU, 3 gigahertz, and giga is really to the power minus 9. So nano is just about right. So this is saying in about half a cycle, if something is in L1 cache, it can get the data out. If branch mispredict means that sometimes the CPU will try and guess the next memory address you are accessing. Maybe you're playing a movie and it will assume that, oh, you want to go from the first second to second to the third. If you jump, that means that it will predict wrongly. So computers these days have ways of predicting, and that's one of the ways they can go very fast. So it says if it doesn't predict correctly, it's a 5 nanosecond delay. If it's in L2 cache, it's 7 nanoseconds. And this is for locking. Anytime you encounter locks, it's 25 nanoseconds. And by the way, this thing, I think he called it what every programmer should know. I think, yeah, it says latency numbers every programmer should know. If you're doing locks and so on, it says about 25 nanoseconds to grab a lock. If you, or unlock it. Main memory, 100 nanoseconds. And then you can see it's sort of growing sort of exponentially when it's zipped. But I'll jump down to here. Reading from memory, 250,000 nanoseconds. So compare that to, and remember, I would put the speed for accessing registers at about less than half of a nanosecond. Okay, so compare the speed of accessing memory. This is 250 nanoseconds to like something better than this. That's a register. You can see it's still increasing. And it says solid state drive 1 million nanoseconds. And on this side, it tries to give you in microseconds. And then you have a disk seek. That is, now we've gone to the hard disk, not an SSD, but a disk that has a spinning platters and so on, spinning plates. The regular disk that sort of make those buzzing noises when you turn it on. And you're seeing that for those disks, you're now going to 10 million, right? And reading, so that's a seek and a read, and it has to actually do seeking and reading to read from a disk. Solid state drives, yeah, you can read the data right there. And here is, if you have a data center with good networking, it's saying round trip within some data center. So sometimes you have many computers in the same rack, and it's able to move data from one place to another. So sometimes it may actually be faster to move data from one computer to another through a very fast network. And then you have also the idea that these days you have this idea of distributed computing, cloud computing, and data is also moving from one city or one country to another country, from one location to another. And that was also here, 150 million nanoseconds. So you can see the exponential time it's taking the further data is away from the CPU. So I'd say the CPU is at the top and everything else slows down. Now there is another site I found, wondernetwork.com pings, and it's showing speeds between different countries. And I think I tried to add Cairo. I couldn't find Ghana. We're in Ghana, but I couldn't find Ghana. You could try and add source cities. Not all the cities on the planet, but at least it has a few, the data they have. And it's showing you speeds between different cities. So for example, it says Cairo to Cairo, negligible, but maybe Cairo to Tokyo, that's the speed, min and max. You can click to view details. So you can explore these. I am hoping that this gives you an idea of why the operating system would want to manage memory, because if it can make it a little bit faster or has some strategy for it, then the processes would seem to work faster. Okay, so at least I am presenting these to you and you can investigate further, right? So now if we look at memory, one of the main things, and we said this in chapter 1, the main thing that the operating system wants to do is to protect processes so that one person or one process doesn't steal information from another process. Even reading can be bad. So for example, imagine if you are trying to log into a website and you typed something, your password. It will be very bad if another program that's running can just be reading the temporary variables that are storing your passwords before it's sent, right? So in order to do that, what most operating systems will do is they keep track of the memory ranges. So it knows that, oh, this process, maybe your operating system is working from 000 to 1999, and maybe your text editor also has a range of memory it's working in, your internet browser has a range of memory. And what it does is every single time it just needs to check and make sure that you are within your range, right? You can think of it in any way you want, but however you decide to do it, the OS just has to make sure you are within your range, right? Now currently the simplest way they do is they keep track of a base address, that is the lower point, and a limit. So for example, if your range is going from 000 to 0119, the base is all 0, and the limit, that is the offset. The textbook keeps saying limit, so some people think that it is the upper bound, which is this. Sometimes it is the upper bound, but sometimes it's not. So for example, if your range is from 4000 to 6000, your base is 4000 and your limit would be 2000. Sometimes there's a less than or equal to, so just pay attention to how you designed your hardware. Some people are going to be doing VLSI or COA, computer organization. If you're doing hardware, just pay attention to your less than equal signs, those boundary conditions. I think I made a mistake here with this one. Maybe it should have been something like 1999, but just watch your boundary conditions. Now, when processes are running, there are two ways that addresses can be calculated. One is to have them be absolute, and another is to have them be relocatable. If you've done any type of programming, and I think a lot of people have done web programming, so I'll use that as an example to start with. Now, what most people are used to when they are designing websites is they can make a link and they say, I have a link, and so for example, this is an absolute address, so it means he knows exactly where it's going. There are other links that are relative. So for example, I would say .. home index.html, right? Or even href. So these are things that we already know about. The idea of absolute addresses. So for example, this is absolute, and the idea of another type of absolute address, at least as far as web design goes, would be to say usually when you say slash, that means a root. So /home/index.html. This would mean go up one directory before you go into home. So we do have this idea of absolute and relative, even in command line. Let me get an example with command line. Even in command line, someone would say an absolute address would be something like change directory to, and you spell everything out. Oh, sorry. Suppose it depends on whether you're Windows or Linux. Let me just see why that didn't. I'm not sure why that. Oh, it's users. Okay, so this is an absolute address. I think they should also work depending. Yeah, both work. Great. So there's this idea of absolute and there's this idea of relative. So you guys are already familiar with the idea of relative and absolute. When you come to processes, the same concept applies. Now when a process is running, the addresses that it sees, so if it has variables, if it has functions, the addresses it sees, it can look at it in two ways: the absolute and the relocatable, or sort of the relative. absolute meaning this is exactly what it means in physical memory, your physical memory. And relocatable is, yes, it can move from one location to another, and that's of the relative address. Right? So usually a relative address is with respect to some initial location. So when I say with respect to some initial location, when I did I had command prompt, I did cd dot dot, it knew that I was in users primus, so it goes up one directory. And if I say, so depending on where you are, things mean different things. So if I'm in a location, relative just means relative to where I am, right? Then the same thing applies in processes. Now I compiled well, this is a small program. In some, it's a function that does an addition, and there is a program that asks a person to enter two numbers, x and y, and that's an addition. And when I use a debugger and I pause this, it says I have four variables, p, x, y, z. X, y are the variables I read from the user, and z is the summation of the two variables. P is just a class that contains the function. And I'm saying, for example, assuming that p is stored in some location, y in another location, x and so on, how do we sort of, and these are the absolutes, so it means that the program is currently in a specific physical location from 8,000 to 9,000. And so based on those, it's been given all these addresses. What about relocatable or relative addresses? And it just means I have to say whatever is my the base plus an offset. And so the base was 8,000, the offset is 10. So p can be seen as relative to wherever I was, 10. X is relative to wherever I was, 11. Y means relative to wherever I was, 12. And Z means that if this program were to move from 8,000, 9,000 and moves to a place like 10,000 to 11,000, that means the P address would also shift along as well. And remember that processes move in and out of memory. So when we say an address is relocatable, it means that it's expressed in the form where it's relative to some location in the program, allowing the process to move from one location to another where necessary. Right. And this is the example I was asking. So if we went to 11,000, 12,000, what would P, X, Y, and Z be? That's just something to think about. Now, when it comes to code, so this idea of memory addresses, so that means your variables, your code can be moving, and the question is, looking at how programs are created, what types of addressing is possible? Now, if someone says at compile time, this was supposed actually to say binding. Okay, so we're supposed to bind data. Binding would mean that we are going to assign your variables or your locations to some addresses. If we do this binding at compile time, often it has to be absolute code, because at compile time we may not know. The only thing we can bind to is, so at compile time someone says, when you're compiling, I want to know the address. That's the idea of binding. I want to know what the address is. But if you're going to do that at compile time, the only thing you can do really is to do absolute code. Now, another strategy that processes or programs can use is when you are loading. So when someone says start a new process for me, when you are bringing the process from storage into memory, then you can figure out what the addresses are. You can figure out whether you want to go make it an absolute, or that's calculate and make it absolute, or come up with some relocatable strategy. And there are other software, other programs that would wait until execution time. It's only when they are running that will try and figure out what was the base and what is my offset before they access the variables. Right. So these are just three different times when you can bind your addresses: at compile time, at load time, or at execution time. That's when it's actually running. Now, I want you to think of this idea that there's, well, so we are repeating the same thing over and over: the physical address and the logical address. So logical meaning this is what the program sees, and physical means this is what it actually is. Now, most of the time there's this register. So there are many registers that are in the textbook. Almost every type of value I have in here that I'll talk about, usually there's a register that stores it, that helps make the computation quicker, right? So there's this idea of a relocation register. Now I'm going to go up 3 slides, and the idea was anytime I had a variable and I wanted to figure out the location, I had this register, this base address, in this case they call it a relocation register, which is used as an offset. So I say, okay, that's the starting point, and then I add my extra shift, and then I get the new address, and that is what is being called relocation register. So let's move to relocation register, and there's special hardware usually on the CPU chip that would do this this whole moving stuff for you. So that means, and that was the example, if I have a variable, it would look at the variable and say, well, what is my base or relocation, and how far do I want to shift it? And this is a diagram showing you that if you have a CPU that generates a virtual address, because remember what the CPU is doing is it's executing instructions from your program, and so that means if it gets an address and says, oh, I have this address, anytime a program is being loaded into memory, every time, so remember the operating system is going to be switching from one process to another for every process that loads. For example, if I'm doing Notepad will have its own relocation register. If I'm doing Word will have its own relocation register. PowerPoint would have its own relocation register. So every different program that loads, depending on what it's up to, will have a relocation register that would move or help shift the addresses, the virtual addresses, so that they can know exactly where in physical memory these addresses point to. Now the other thing, so there are many topics in memory management. One of them, or at least that you have to start thinking about, is linking. And when you talk about linking, they mean putting different parts of a program together. So you'd have maybe different libraries and so on. How does it put them all together? And this idea of I think I said absolute code and a relocatable code repeats itself. So this theme just keeps coming over and over. I think memory management should just be called absolute to relocatable, and how do you map them, because this idea keeps coming up, right? And what we have here specifically is that we have the idea of dynamically linked libraries and statically linked libraries. So when we say a library has been statically linked, that means that it's usually been compiled and merged with the code. For dynamically linked libraries, that means that several processes are going to be sharing some code, and that would mean when the program is running, it would pull up the library and figure out how to merge it into what is currently running, right? And the idea of dynamic linking is, for example, I have an instruction that says x is equal to a stub that sums 2 variables, and that means when it's called, it's actually going to, so the instruction would say x is equal to sum stub. So we wouldn't call the functions directly. The idea with dynamic linking, because we haven't, since they are sharing the same code, it wouldn't have the exact function. But instead, when you make the function call, this function will then go and figure out, oh, is the function that I'm sharing in my memory space? If it is, then it can go and search for it and replace it with the function proper. But if it isn't, then it would have to go to storage, pull it in, and load it, right? So I'll do a demo in class showing this, right? Or should I do it now? Okay, let me see if I can do it now. So in a directory, I currently have an executable. It says bash, but it's Windows. Okay, so I have an executable that would ask, this is the program I was talking about before, ask the person to enter 2 numbers. So let me run this. So ask you to enter a number x and a number y, and then it says library version 2 is doing the addition, right? And the sum of x plus y is 30, right? Enter. Now watch carefully. The only thing I'm going to do is copy class library sum1 version3.dll. DLL means dynamically linked library. I'm going to copy this to that's all I did. I just overwrote a specific file with another one that says version 3, and I'm going to run the same program. So watch what happens. Same 10, 20, and now it says library version 3 is doing addition. So the idea is that it's the same program that's running. So let me do an ls again. It's the same program exe that's running, but when exe is running, it always looks to this file and tries to find what function of summation has been implemented. And I have about 3 different versions of the file, of the library. So you can have all these functions in DLLs. And that means when it's running, it will actually figure out, oh, what's the name of the function, and does it exist in there, and then it pulls it in and calls it. And that's why I'm getting, in one case it says library version is doing addition, and in another case it says library version 2, library version 3. So that's the idea of this dynamic linking. So as the program is running, it will figure out, do I have the function? If it doesn't, it goes, pulls it, and executes it. I'll talk about swapping, but I think I've done a lot of talk about swapping, so I'm going to skip the swapping talk. Right. Now let's discuss, and we've talked about this already. So what this chapter, we just keep repeating the same things, is how do we make sure that you are not accessing data that is outside your range? So what usually happens is whenever the CPU has a virtual address, it's going to compare. Remember I said there's a base and a limit register. So base is the lower point and the limit is the maximum offset you're allowed. So if you're doing any computation, you would say, well, check against the limit to make sure that I am within range. If I'm within range, it means I'm good to go. So yes, it will then add my relocation. If I've gone beyond the limits, then I have an addressing error. Right? So this is the simplest idea, or the simplest approach to this. Actually, this should be 1,000, not 9,000. Yeah, it should be less than 1,000. So please make that correction. I'll make it in the slides. Okay, so that's the idea for checking the memory addresses. Now, when a computer is dealing with memory, so we've talked about this idea of we have memory, can be absolute or it can be dynamic or relocatable. And there's this other idea of we have these base registers, and well, let me go back to that slide. There's this base register and limit register, and we have the idea of we can relocate the virtual addresses as we see them. But all of this doesn't help if we don't even know how we're dealing with the memory. And the simplest approach is we can break memory into fixed partitions. So if I have 2 gigabytes of memory, I could break it into maybe 1 megabyte blocks or 10 megabyte blocks. So the idea is we can break memory into fixed partitions, or we can have variable lengths. This is a lot like when we're discussing maybe in databases or linked list arrays, other forms of storing data. We can always say we can decide to have a block of or a section of memory or hard drive for something, or we can have maybe a variable length where we say, oh, this is the starting point, that is the ending point. So this idea we've been seeing in computer science, and again it comes up here. We can break memory into fixed pieces, or we can have variable pieces. Right. So let's look at the fixed pieces approach. If memory, so on my left I have fixed pieces, so I have all of my memory, and I think in this case I'm breaking them into, so from 0 to 500, 500 to 1,000, 1,000 to 1,005, 1,005 to 2,000. So I've broken the memory into fixed pieces, and for any process I can assign one of the pieces. So for example, the OS has 4 pieces, the text editor has 2 pieces, internet browser has these 3 pieces, and so on. Or I could also just specify a range. So for example, I'll say the OS goes from 0 to 1,500, the text editor goes from 1,900 to 2,305, and the internet browser goes from 2,900 to 3,890. These numbers just means it's not a fixed number. That means that the ranges just vary wildly. Any size you want, we can give you a piece. right? So you can think of it maybe the way we purchase land. I don't know where you live, but maybe you purchase land. Is the land broken into squares, or you just specify any range you want and maybe they give you a piece of the land? Or maybe well, that's the simplest example I can come up with. I'm not going to do too many so I can get going quickly, but at least you have this idea of, there's this idea of fixed partitioning and variable length partitions. So fixed partition means we take the memory, break it into equal slices, and we give you as many slices as you need to accomplish your work. Of course, you can see if we have fixed slices, it means that maybe somebody isn't going to use all the slices. So for example, if your text editor was using just 501 or 502, we have to give it 2 slices. So the fixed scheme does waste space. And if we're given it variable length partitions, then we can just specify a partition for you and you wouldn't have to waste any space. So the advantages, disadvantages, as usual for all of CS between fixed and variable length things. Right. Now, when we are breaking up memory as well, requests will be coming in. Someone will say, I want to have some amount of memory. There are usually 3 strategies we can use: first fit, best fit, and worst fit. And I'll illustrate with an example. So on the left we have partitions. So memory has been broken up into all these partitions: 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and so on. Let me move this up a bit so I capture the 27th. Okay, so memory has been broken up into all these partitions, right? And the idea is, what if someone says they want 4 partitions? The white partitions are the ones that are empty. Of course, the OS is using these 2, text editor is using this, internet browser is using those 2, command line is using that one. If I want 4 partitions, first fit means that I'm going to go from beginning to the end, and the first space I find that would be contiguous and I can put my data there, I place it there. So 4 partitions, I can say, oh, here's my first fit: 4, 5, 6, and 7. For best fit, the idea is to find the space. So there are 3 big spaces: 4 to 9, 11 to 15, 18 to 24. Find the space that is closest in size. And this one, I think 11 to 15, that's 5 slots, is closest in size to 4. If I found 4, I'll give it, but I can't find 4 exactly. So best fit, I'll put it from 11 to 14. And of course, I'll make a whole of 1. So anytime you put something in, I'll have leftover. And worst fit, the idea there is you're going to put it in the biggest space you can find. So worst fit in this case would go here. Now, let's say someone wanted 2 partitions. If 2 partitions, first fit would go in these first 2, because that's the first I found. But best fit is also these first 2, because 2 is closest in size to 2, which is better than putting it in this large space or that large space. But when it comes to worst fit, I again put it in the largest space. And the advantages and disadvantages, the text would expand on that. But usually for first fit, tends to be the fastest, easiest thing to do. Best fit, you would have a lot of little leftovers, but you are hoping that the leftovers are not things you'd be using a lot. But worst fit, of course, best fit, if you found the exact fits, you will not have any waste at all. Then the waste you'd hope are these small leftovers. And the idea of worst fit, so for example, consider if I put the first request 4 into here. That means that I actually have leftover of 3, which is a very large block. So worst fit means I try and make sure I have very big holes all the time. That's the idea of worst fit. And if you read the text, I think that's how it's being described: first, best, and worst fit. There's also the idea of external and internal fragmentation. So I would go up to when we had the fixed partitions and the variable length partitions. Remember what we said with fixed partitions was it's possible that if I give you a large amount of space, because they are fixed partitions, and I'm not doing 1.5 or 1 1/4, I'm giving you 1 partition, 2 partitions, 3 partitions. It's possible that you will not be using all the memory. If you don't use all the memory in the space I give you, usually it's called internal fragmentation, because there are all these fragments that are internal to the processes. And external fragmentation usually occurs with variable length partitions, or it can also occur with fixed length partitions. But the idea is that the unused spaces are occurring outside the processes. So in simple terms, internal fragmentation would be fragments of memory that are unused they have been assigned to people, but they are all these little pieces that are used within a process's memory space. And external fragmentation are those little memory pieces that are left outside of processes. Now, sometimes it can happen that you have a lot of memory, but you don't have continuous memory. It's all in little pieces, like 1 megabyte here, 1 megabyte there, so many pieces of megabytes. And if you put them all together, you can actually have enough space to give to someone, right? Now, usually what we do is we can do compaction, which means that we move the code of the processes closer together. So by compaction, I would mean that I'll move OS up to the first 2 slots. 10 would move to partition 3, 16, 17 would move to 4 and 5. So compaction means I would try and move them closer together so I can make space. And while you're moving, trying to do compaction, remember that you can't do compaction if the code is absolute. So if code has been compiled to be absolute, you can't move it around. And if it was load time and so if they bound it to absolute addresses, you can't move it around. And if there's a process that's working on memory, currently running, you can't move it around, because if he's thinking of storing information and by the time he comes back you moved his memory from one place to another, it's going to crash. So those are some issues. Now that means that anytime we have an address, we can break it into 2 parts: a virtual address number and an offset. And the idea with this, and I'm sure maybe you've encountered this before, there are some hotels, for example, or some offices that when you enter, they would say, oh, this is room 101, meaning it's on the first floor, it's the first room. Room 206, second floor, 6th room, and so on. So I'm saying, imagine if you had a hotel with 100 rooms per floor, and there were 5 floors. That means that if I wrote 1011 as a room number, it would mean that it's on the first floor, room number 12. Okay, and a room number 3089 would be on the 3rd floor, the 89th room. So this idea of embedding the location and offset is something we already do. So on campus, our own campus, we have room numbers like 217. When we hear 2, we know that it's in a certain block, and when you hear 17, we know where it's supposed to be. Even the offices, I think I'm in office 209, and it even starts with E. So when you hear E, you know it's engineering block. 2 would be 2nd floor, and I'm sure you can come up with other examples where numbers actually would point you to locations and where exactly in those locations. This is another example where I'd say it should also be possible, for example, to say if 2 events were happening in the hotel, we could say, oh, the first floor for the event, so for example, an operating system conference, we'd say, oh, the first floor that we are using as far as the conference is concerned is the 4th floor, and the 2nd floor with respect to the OS conference is the 5th floor. And we are having another conference, maybe database conference, and we'd say for that database conference, the 1st floor is supposed to be the 2nd floor physically, and the 2nd floor is the 1st floor. So there's this idea that we can map. So depending on what you are working with or your context, it would match you to different locations, right? And this mapping is what I've done here. So for example, there's an OS process that's running, and virtually has these virtual numbers. When it's 0, it means for physical 0, for virtual 0, go to physically to 12. 1, everything that is supposed to be in page 1 should go to page 0. Everything in 19 should actually go to 2. Everything in 20 should go to 1. So the idea is now, whenever a process is running, the page it's working with, that's the partition it's working with, is going to be mapped to a physical location. And that means that we can, when we move something from one physical location to another, we have to update this lookup table. So the idea is we have a lookup table, and as we assign things, we also keep track of where we've put them, right? This is a little bit like when you're entering a supermarket and you give them your bag and they put it in a location and give you a number. So every time you come back, they give you a number. And so for different things go into different locations, right? And okay, I think the question here was, and I think it's good if you know some binary numbers. So these virtual numbers, so 0, 1, 19, 20, these are the binary equivalent. So 1 is 0001, 19 is 10011, 20 is 10100. And what you'll be seeing in the textbook is sometimes you'll be given an address. And remember, an address usually is composed of a partition number. So we have all these partitions and an offset. So it would say, oh, when this is my address, so 1001101, how do I find this? Some part of it represents your partition number and some part represents your page number. So this is on page 10011 is 19, offset 101, and 101 is 5. This address is 1011011. 1011 is 20, and the offset is 011, that is 3. So you can have this idea of, you can, anytime you're given an address, map it from one location to another by looking at what the partition number is and what the offset is. And of course, when you look at the virtual number, so 1011, you can also tell what the physical address is. So going from a logical address, you can also go to a physical address. Okay, so in the second example, the data has been stored in different locations. And so if I ask you, for example, where is, this is like OS character, I think that's L, or is that an I? Not sure. But I think this is a W. So for example, text editor has a W. Where is the W stored? You can look at the text editor, which is the green locations. Hello world, that means physically it's stored in 0011. That's the partition. And which character? 0, 1, 2, 3, 4, 5. So it will be 0011, and the offset is 101. What about this internet browser at F? The internet browser are the blue ones, and the only F is here. So for example, the address for that one will be 0101. Sorry, 01010, and then F is at 0, 1, 2, 3, 4, 5, 6, 7. Location 7, and 7 is sorry, head is not working straight. 7 is 111. Okay, so those are the examples. So if you're given an address, you should be able to figure out the virtual number, the offset, and figure out which of the physical addresses it goes to, if I've given you a mapping from the virtual to the physical addresses. And if I give you a specific location or some data, you should be able to look at the mapping and work back what the virtual address is and what the physical address is. Okay, so I'm going to break this video into two parts. I'm going to record in the next part. I'll talk about segmentation, paging, and at least 3 paging strategies.